Hello, this is Professor Muhammad, and this is analysis of statically indeterminate structures. And I'm going to talk today about an introduction just for this course. Just I want to highlight something that this is a kind of a course for our undergraduate students, and this course titled or coded with CAL 3005-41 in SKKU. So this is the code of the course, and this is the title of the course, Analysis of Statically Indeterminate Structures. I'm going to just have a look on the important issues regarding the course description and main objective and the communication with me in general. And after that, I'm going into the contents of the class, as you are going to see here. So let's start with the title and some information about me so that you can communicate easily with me. As we said, this is the title of the course, Analysis of Indeterminate Structures. This is CAL 3005-41. There is another one, of course, which is called the structure analysis, similar to this code. So take care of the code when you are registering for the class. My name is Professor Muhammad Noureldin, and my office in the 4th floor in the engineering building 1, and this is my contacts. Let's go now to the course description. Actually, this course is very important for those who are interested in structural engineering in general. One of the most important courses and classes that any engineer or any structural engineer, even civil engineer, should always have and at least learn the main and the basic principles of this important course. So this course introduces methods of analysis for structures having a high degree of static indeterminacy. This is one of the things. Let me highlight here. I'm not sure why the highlighter not working. Yes, let's go with this. Not sure you can see. Okay, cannot see. You cannot use this highlighter now. Okay, again, it is the course introduces methods for analysis for structures having high degree of static indeterminacy, such as continuous beam, trusses, plane frames, and multi-story frames. This is an important thing that we should always keep in our mind, because whenever that we think about the structures, we think about them as if they are determinate structures. But actually, the reality is different than this. Most of the structures around us, they are indeterminate structures. So this is why we're going to encounter in this class the real structures that is really there, out there, that we are seeing. Whether they were like plane frames, multi-story frames, beams, trusses. So this is an important issue that we should bear in our minds. The general objectives are for the students, like a bunch of objectives here. I'm going to summarize them. First, we are going to identify, formulate, analyze, and solve structure analysis and design problems involving statically indeterminate structures while working individually or function on a team. This is something very important for me, because sometimes I'm going to assign some teamwork for a group of students to be assigned a certain task, and they are going to fulfill it. So you are going to find yourself working individually, sometimes working in a group or with a team, and actually this really what will happen for you, or what you are going to go through after going into your real life career. Another objective is to combine knowledge of statics, elastic deflection, and comfortability gained in previous courses to understand and apply classical methods. Actually, previous courses here means that the structure analysis, okay? And apply classical methods for the analysis of statically indeterminate trusses, beams, and frames. And then we are going to improve the communication skills by documenting design decisions and coherent and legible design calculations. We're going to develop awareness of contemporary structures. Actually, this is something important. We're going to take some exposure to some recent or some structures, and we are going to have thinking about how these structures are being analyzed. Okay, and we're going to understand this some complicated contemporary structures. We're going to recognize the need for lifelong learning to keep abreast of new design and construction methods, enhance one's abilities as a designer. This is very important for the student, that you are enhancing your ability as a structural engineer or a civil engineer, and maintaining one's professional competence. Okay, now let's jump into the main, contents, and this is the main syllabus of our course. As you can see here, we have like 15 weeks. The final week number 15, it's the final exam. There is no midterm exam, and we are having different, as you can see, different contents here. The contents actually is going to be, I think, very interesting for anyone who really wants to learn about indeterminate structure. We are going to start with an introduction to statically indeterminate structures. So we are going to talk about the pros and cons, the advantages and disadvantages of indeterminate structures, and analysis of indeterminate structure, the main assumptions involved. And then we're going into the approximate analysis of rectangular building frames. We're going to figure out what are the main assumptions for the approximate analysis, and then we're going to talk about three of the most commonly used analysis methods by engineering. I can say by no far they are like the most common methods that you need to learn for yourself or to at least to equip yourself for a long life career. You're going to use the analysis of vertical loads, okay? You're going to use the analysis of lateral loads, which is comprising the portal frame method or portal method and cantilever method. We have two methods for the lateral load and one like the main simple vertical load or analysis of vertical loads. They are the most important ones, and you are going to like keep them in your mind even that after being graduated. And we have after that the method of consistent deformation. We call it the force method. We have like 4 avenues here. We have structures with single degree of indeterminacy. This is the simplest one that you could see. And then internal forces and moments as redundance. We're going to talk about this. Structures with multiple degrees of indeterminacy, and then support settlements, temperature change, and fabrication errors. We're going to think about, or we are going to take into consideration these kind of settlements, temperature change, and fabrication errors, how we are going to take them into consideration in our analysis, which is something very important. We are going to think about also are going to study the 3-moment equation concept. We're going to apply it and see how we can use it and apply it in different methods. We're going to talk about the method of least work, and then we're going to, these are the force methods. Now we're going to slope deflection methods, which is related to, we're going to talk about basic concepts of the slope deflection method. We're going to talk about analysis of continuous beams, and then we're going to take exposure to frames without side sway and frames with side sway. So these are the two very important analysis or methods that you should learn, okay, for the frames with and without side sway. After that, we're going to talk about moment distribution method, considered to be, we're going to talk about this in detail, but just it is a brief contents, so I do not want to dig deeper into each point. Moment distribution, one of the most and famous method for solving indeterminate structures in general. We're going to talk about the basic concepts behind it, and after that we're going to talk about the analysis of side sway and non-side sway frames. It's similar to the slope deflection method. After that we have a final exam. For the evaluation, I'm going to give like for the attendance, as you can see, heavy mark is going to be given to the attendance. In class assignment, I'm going to give you some in-class assignments, which is 25%, and home assignments, it's 25%, and then the final exam is going to be 30% as a portion of the total grade. So don't worry about this. If you are going to attend and you are going to work hard during the class and making your home assignments, then you are going to achieve a very high grade, I guess. The main textbook that we are going to rely on is going to be Structure Analysis by Aslam Kasamali, 4th edition. We're going to use this as the main textbook for our class. So be sure that you have a copy of it, or you can at least start. We are going to start from chapter 12, I guess. So from chapter 1 to chapter 11, it is covered by Structure Analysis course, which is supposedly that you have had it before. But for this, you are going to have, or we are going to work from chapter 12, okay? And the course would be recorded via iCampus, and I'm going to upload these classes also on YouTube. So you need to subscribe in my channel, and you are going to be notified with any new videos that I'm going to upload. Okay, nice up till now. Let's go to the introduction to our let's go to the introduction. Okay, so now for the introduction, we are going to talk about some issues. This is the introduction. Okay, introduction to, I'm going to let you have this materials, okay, so don't worry about this. Okay, so let's have an introduction here, which is related to the statically indeterminate structure. Actually, I want to highlight something, that whenever that we're talking about the determinate structure, so statically determinate structure, okay, we are talking about equations of equilibrium, or equilibrium equations, okay? So commonly, whenever that we have determinate structure, there is equations of equilibrium there, and we can solve our structure using this equilibrium equations. And if it includes any equations of condition, if we have internal hinge or something, we can solve it. So our structure is mainly determinate, and we are going to rely on equations of equilibrium and equations of conditions, if any. Okay, equation of conditions means that whenever that you have like a internal hinge, for example, okay, so this case, that this internal hinge is going to give us an equation, additional equation, which is the equation of condition. And then beside the main unknowns, or we have like 4 unknowns for our structure, if we're going to talk about this simple beam, this beam, okay, hinged beam, then we have 3 equations of equilibrium plus 1 equation of condition, which is provided by this internal hinge. But for the indeterminate structures, which is our case, which is our class, indeterminate structures have more support reactions and or members than required for static stability. So the equilibrium equations alone are not sufficient for determining the reactions and internal forces of such structures, and must be supplemented additional relationship based on geometry of deformation of structure. This is what we're going to talk in detail, okay? So that's what I want you to understand, the concept here, that equation of equilibrium are not going to be enough for us. We need to use something else. We need to have more equations. What are these equations? They are going to be provided from the geometry of deformation of the structure, okay? We're going to use about, we're going to talk about the comfortability concept. We're going to talk about the force deformation relationships, and you are going to find that really they are like providing more equations that is going to satisfy, or at least going to help us in top of, or in addition to, the equations of equilibrium. Okay? Okay. The additional relationships, which are termed comfortability, that's a very important term that we are going to use it always, okay? Comfortability conditions ensure that the continuity of the displacement is maintained. So again, what is the meaning of comfortability condition? It means the displacement, okay, the continuity of the displacement is maintained through the structure, and the structure's various parts fit together. What is the meaning of this? For example, let's take an example here. Look to this point, which is point D here, okay? Before the application of the load, we can see that all the structure is in its like original position. But whenever the load is being applied here, you're going to find the structure is having this deformed shape. Look to the point D. You're going to have that there is some deformation happened here, right? And there is some rotation took place here. And there is some like out of plane, or we can say some small deformation that is took place perpendicular to the member AD, right? So there are things here. We can see that we have like 3 members already like joined together at D. So we have, this is, let's assume this is point D. We have one member which is member C, D. We have another member which is member D, E. And we have one member which is member AD, right? This is the point D. This is what we call the comfortability condition here. Comfortability means what? Simply by giving the example, which is at a rigid joint, the deflections and rotations of all the members meeting at the joint must be the same. Simply, this is what I meant by the comfortability condition, okay? That the displacement that is going to take place, okay, in this member, okay, definitely it is going to affect the member DC or DE, and definitely is going to affect member DA because they are joined in one point. Okay, so the design, I'm not sure why this is appearing, but anyway, the design of an indeterminate structure is carried out in an iterative manner. What is the meaning of iterative manner? Simply, this is similar to what you have done before in structure analysis course. You're going to assume the member cross sections, and then you are going to analyze them and then check whether the cross section is going to fulfill the loads or not. And then you are going to repeat it again. And this is the meaning what I put it here. The design of an indeterminate structure is carried out in an iterative manner, where the sizes of the structure members are initially assumed and used to analyze the structure. And the initial forces obtained are used to revise the member sizes or the member sizes. Okay, so this is summary for what I was talking about, which is the comfortability condition. Okay, let's go through the advantages and disadvantages, okay, of this system. Let's start with the plus or the advantage. We have like 3 main advantages here for the indeterminate structure: smaller stresses, greater stiffness, and redundancies. Okay, we have three different advantages. The first one is smaller stresses. What is the meaning of it? Assume that we have like this is statically determinate beam, and this one, as you can see, it has fixed support, so it is statically indeterminate beam. Okay, and we have the same loading, which is W here and here, and this beam, which is hinge roller, it is going to be deflected under this load, and this beam, which is fixed is going to be deflected under the same load, okay, under the same force. Okay, let's have a look here. Okay, let's have a look here. If you look, first of all, the maximum stresses, where the maximum stress is going to occur? Exactly, at the middle. This is the maximum stresses or the bending stresses that we're going to talk about. If we're going to draw the bending stress or the bending moment, okay, the bending moment diagram for the determinate structure, you're going to find that the maximum bending moment is going to be WL squared over 8, as you can see it here. This is the maximum bending moment. But if you go and draw the bending moment diagram for the indeterminate structure, you're going to find that the maximum bending moment is going to be WL squared over 24 at the center, and at the fixed supports, it's going to be the maximum moment is going to be WL squared over 12, and it is having a minus sign. So definitely the maximum here is higher than the maximum here. This is the meaning of, sorry for this. This is the meaning for the maximum stresses in statically indeterminate structures are generally lower than those in comparable determinate structure. Okay, do you understand this? So this is number one. The stresses is going to be or are going to be smaller. Okay, let's jump into the second advantage. Greater, this is what we call it, greater stiffness. What is the meaning of this? Stiffness, whenever we talk or say anything about stiffness, we mean deflections, okay? It is like the synonym of deflection. Look to the deflection here. If we're going to use elastic methods to calculate the deflection, it is going to be 5WL to the power 4 over 384 EI. However, here it is going to be WL to the power 4 over 384 EI. So as you can see, almost this one is 5 times the indeterminate deflection. Okay, so we can see how really we are having a great advantage here. From the figure, we observe that the maximum deflection of the indeterminate beam is only 1/5 of that of the determinate beam. Okay, so this is something considered to be the second advantage. Okay, let's go to the third advantage, which is the redundancy. Let's also compare two things, determinate beam with indeterminate beam. Okay, here this is determined because we have roller here, roller hinge here, and we have roller here, and we have internal hinge here. However, here there is nothing, there is no internal hinge. So this is considered to be indeterminate structure. We have two reactions here, one reaction here, one reaction here. It is 4 unknowns, and we have 3 equations. So this is one statically indeterminate. If you look to what will happen if we remove the middle support, remove this here, and remove this. What will happen for the determinate structure? Exactly, it will be unstable. As you can see, it will fail. But for the indeterminate structure, nothing will happen. Even that we remove this one, nothing will happen in the middle because it is going to stand still or going to have its stability maintained. We call this statically stable structure. Statically stable structure. Okay? Okay. Let's go to the disadvantage now part. We are dealing with 2 disadvantages only. The first one is related to the stresses due to support settlement. What is the meaning of this? If you have like determinate beam here and indeterminate beam here as a comparison, you're going to find the one that is having the internal hinge, which is the determinate one. Whenever this support is going to settle down, as you can see here, there is no additional stresses would be developed in member AB and member BC. But look to this, if this joint, okay, goes down with deflection B, you're going to find that this point is going to make what? Some like stresses here and here in the beams. Okay, you can feel it. I think that if you have like 2 rulers, okay, rulers, they are like linked together at this point. Easily you can like let them go up or down. But if you have one straight stick or ruler, okay, you are going to find if you try to take it down from the middle, then it is going to be stressed. This is what we call it, the support settlement problem or stresses. Support settlements do not cause any stresses in determinate structure. This is the advantage of determinate structure. They may, however, induce significant stresses in determinate structure. Okay, let me use the highlighter better here. Okay, so they are going to have significant stresses for indeterminate structure. Okay, okay. Let's go to the next one. Let's go to the next one. Okay, stresses due to temperature changes and fabrication errors. Yes, whenever that you have determinate structure, this is determinate beam, and this is indeterminate beam, okay? So for the determinate beam, if there is change in temperature, there is, as you can see here, some excess or like elongation. We call here, this is elongation, because this is a roller, so the roller allows any movement in the horizontal direction. But if you look to this one, which is the fixed beam here, which is the indeterminate case, it will not allow any additional elongation. The additional elongation, whenever that we have change in temperature, is going to be, as you can see here, which is alpha, okay, coefficient of thermal expansion, delta T, which is the change in temperature, and L, which is the length. Okay. However, here there would be no forces will be developed in the determinate, but in the indeterminate, forces will be produced. It equals to alpha times delta T times AE. Okay. So now we can state that, like support settlements, these effects do not cause stresses in determinate structure, and this is the advantage of determinate structures, but may induce significant stresses in indeterminate structure. Okay, so this is an important issue regarding the disadvantage of the indeterminate structure. Okay, let's go to the analysis of indeterminate structures. We are going to have some assumptions, and we need to understand these assumptions. Okay. Fundamental relationships that we want to understand. Okay, there are some fundamental relationships that we want to understand. Regardless of whether the structure is statically determinate or indeterminate, its complete analysis requires the use of three types of equations. So we have three types of equations that we need to use. First, it is equilibrium equations. Second, member force deformation relations. Third, comfortability conditions. Three different relationships. We need to maintain them. Okay, I'm going to talk about each one of them in detail in the next slides. Okay, now let's go with this. Let's start with the equilibrium equation. Actually, the equilibrium equation relates the forces acting on the structure or its parts, ensuring that the entire structure as well as its parts remain in equilibrium. What is the meaning of this? Let's have a look on this two-hinged truss. Okay, you're going to find that there is point B, C, they are hinged. Point A, there is as if an internal hinge here. And equilibrium equation means that the force that is going to be developed in member AC and member AB should maintain the equilibrium condition. What this equilibrium condition means? If we are going to take, let's take the summation of f of x, or the horizontal force here, f of x equal to 0 at this point, which is point A. We're going to assume that the horizontal direction is positive. Okay, then if we are going to look to this, we're going to find that here, sorry for this, let's have the pen. Okay, so at this point we're going to have, like, if we have the forces that is going to be here, we are going to have component here and here, which is component related to the force here. This is force in AC, okay, and this is the force in BA, and we are going to have here some value. If we say this is the force FAC and FAB, and we are going to take the equilibrium at this point, point A, I mean that summation of x equal to 0, then we are going to find that FAB, if we say this direction is positive, then FAB times the component of it, which is, we have the dimensions here. We are going to talk, this is, if you go, this is, you are going to find it theta. So this is going to be cosine theta. So this is cosine theta. So minus, because we are in the opposite direction, minus 0.6 FAB plus 0.6 FC. This is again this component, which is 0.6, and this is here 0.6, equals to 0. From here, we can obtain FAB equal to FAC. Now we are sure from the x direction equilibrium equation that FAB should equal to FAC. If we're going to use the vertical direction equilibrium equation, which is related to Fy, taking the vertical direction to be positive, then we're going to find that 2 times sine theta times FAB. We're going to talk about this one here. Okay. This is 2 because we are going to have another component from the member AC, and we said before they are the same. So we are having 2 here. Then minus 500 because we have 500K here, which is applied. Okay. Then we are going to obtain FAB equal to FAC equal to 312.5 K tension. Okay. This is something that is important to be highlighted. This is the first step for solving this. Actually, this is determinate structure, okay? Take care, this is determinate structure. It's not indeterminate, but the same philosophy applies. The same philosophy applies. So the equilibrium equation, as you can see here, it allowed us to get the value of the forces, the magnitude of the forces in the two members. Okay, we know them now. Now let's go to the second part, which is what? Exactly, the member force deformation relationships. There are some relationships which is dealing with, okay, that is making a relation, okay, between the member properties, forces, and deflections. So we have three different things here. Okay, we call this member force, like member force deformation relationships. This is related to the geometry of the structure. This one is the force in the member or in the structure. This one is the deformation of the member. This is very important equation. We call it the force or the member force deformation relationships. Okay, so if you look here, now we have the components of AC or the forces of AC and AB. Then we can apply it in a very simple way, the two components of them in every horizontal and vertical direction. And we have the 500K here. That's very nice. And we could achieve the values of the reactions as well here at the support B and C. Okay, now we can say to determine the displacement of joint A of the truss, this one here, we first employ the member force deformation relationship, which is going to be this one. Okay. Okay. So actually, this member force relation deformation. It involves the material cross-sectional properties like A, I, and A of the member, and provide the necessary link between the forces and displacement of the structure. Now, delta AB means that it is here. And delta AC, which is the deformation along the member AC, should equal to the force in them times the length of each of them, because they are equal, over EA. Actually, EA, in our example, it is constant and equal to 20,000. Okay, I think this is from the previous slide. Yes, we have EA. It is constant here. Okay. 20,000 K. So in this case, we found that the deformation is going to be 0.313. So now we could obtain the value of this 0.313. And here also it is deformation going to be 0.313. Actually, this point is going down. Let's go to the next one, or the next important relation that is going to make it easy for us. As you can see, this is member C, AC and AB. This is delta AC here, delta AB here, and actually the point is going down, which is A dash here. It was A and then goes to A dash. This is the delta. This is the real delta that is going to take place, or this point A is going down by the amount of delta. Okay, so here, this is what we call it the deformed shape. If you look here, this is the deformed shape, and this is the delta that is going to be, or to take place between, due to the forces applied, which is the 500K. From delta AB equal to delta AC, because of symmetry, equals to, from this simple geometry, we can say that delta times sine theta equal to delta AC or delta AB, and this would equal to 0.8. Sine theta here, it is known for us because we have all the geometry. Then delta AB equal to delta AC equal 0.8. This means that delta is going to be 4.69 if we are going to calculate. From this very simple structure, we can get the idea here that we have three different relation. Again, let's go back here. Equilibrium equation, member force deformation, and comfortability condition. Three different rules based on which we are going to solve our structure, and we are going to get, and solve it means that to know the normal forces, shear forces, bending moments, and even the deformation of each point. Here, this is the equilibrium equation. Here, this is the member force deformation, relating using this kind of the important relationships. We obtained from here the delta of each member. After that, by using the comfortability equation, we can obtain the final delta of the structure. We have known now the forces in the members, the reactions at the supports, the deformation at the tip of the structure. This is what we want to know. Okay, this is the determinate structure. We are going to apply the same for indeterminate structure in detail in the next chapters. Okay. Let's go and finalize our video by the methods of analysis, or the methods of analysis for the indeterminate structures. I'm going to talk globally, or we can say and generally. We have two different types. The first one is the force methods, and the second one is the displacement methods. Okay, so we have two ones here, force and displacements. For the force method, we call it flexibility methods. The unknowns always are the forces. Okay, so the force methods, in the force method, the unknowns are the forces. And generally, the force methods are convenient for analyzing small structures with a few redundants. Redundance means that the extra unknowns that we do not know. This is an important rule that we have to keep in our mind. We are going to deal with that in chapter 13 and chapter 14. We're going to talk about the consistent deformation method, and we're going to talk about three-moment equation and method of least work. These are considered to be the force methods. Okay. The next one is going to be the displacement or stiffness method. Displacement or stiffness method. And in this displacement or stiffness method, we are going to have the unknowns or the displacements. And we are going to deal with it. Actually, this method is very nice for computers. So these methods are more systematic and can be easily implemented on computers, and are therefore preferred for analysis of large and highly redundant structures. They are so systematic. And we are going to learn about them in chapter 16, which is slope deflection methods and moment distribution methods and matrix structure analysis in chapter 18. We're not going to cover this actually in our class or our course, but anyway, we're going to talk in depth and in detail for the slope deflection method and moment distribution method. Okay. Actually, this concludes our class today, the introduction for the indeterminate structure. As I said, it is very interesting, actually, something that we are going to find. It is really interesting for us. You are going to find that this introduction is going to give to you a great deal of understanding of what we are going to do during the class, what are the main important advantages and disadvantages of the indeterminate structures in general. We talked about the smaller stresses for advantage. We talked about the greater stiffnesses. We talked about more redundancy. And for the disadvantage, we talked about the stresses due to supports, settlement. We talked about the stress due to temperature change and fabrication errors. After that, we talked about some fundamental relationships of indeterminate structure. You need to keep them in your mind. And we mentioned about the equilibrium equations and member force deformation and comfortability condition. After that, we took an example, which is a small determinate truss, actually, to show how these three rules are working together in harmony in order to get, at the end, what is our main purpose? To know the forces in the members, to know the reactions at the supports, to know the deflection at certain points. Already we have obtained this using equilibrium equations, member force deformation relationships, and comfortability conditions. After that, we talked about the main different approaches for analysis. We mentioned about two different ways: force methods, which called flexibility, where the unknowns are the forces, and the second is the displacement method, which we call it stiffness methods, where the unknowns are displacement. Okay, thank you, and see you for the next video.